Wind, simply put, is a horizontal movement of air. But is that really all wind is? Well, if the Earth didn't rotate and there was no friction between moving air and the Earth's surface, sure. Air would flow in a straight line from higher pressure areas to lower pressure areas. But the Earth does spin, and there is friction. So wind isn't as simple as we like to think. It's much more important than most of us realize. Let's start with the basics. As I mentioned earlier, wind likes to move from high pressure to low pressure areas. We can think of wind as nature's attempt to balance unequal air pressures that exist on Earth, with solar radiation as the ultimate energy source for most of the wind here on Earth. Since Earth is tilted on an axis, the areas near the equator receive the most solar radiation. The rays from the sun are less direct as we move away from the equator towards the poles. This difference in intensity leads to different temperatures and climates, causing different air pressures and wind movements. Air at the equator will heat up from solar radiation and rise to the top of the troposphere. As it rises, it also moves towards the poles. As this air moves away from the equator, it begins to cool and becomes more dense, dropping back down to the surface of Earth and eventually moving back towards the equator to heat up again, repeating the process over and over again. This motion forms what we call convection cells. There are 3 different types of convection cells called polar, ferrule, and Hadley, all producing different pressure systems and ultimately leading to the differences in airflow. In the northern hemisphere, Hadley cells are between 0 and 30 degrees and would produce airflow from north to south, but really we see wind move from northeast to southwest here due to the Coriolis effect. This area houses the trade winds. Ferrule cells are between 30 and 60 degrees and the air flows from south to north, but again, due to the Coriolis effect, really flows to the southwest. We know these winds as the westerlies. Polar cells are between 60 and 90 degrees and flow to the northeast. We call these winds the polar easterlies. The southern hemisphere has the same cells in the corresponding latitude lines. However, the winds in the southern hemisphere vary slightly in the sense that they come from the South Pole as opposed to the North Pole, and they are deflected in a different direction due to the Coriolis effect. Now, I have mentioned the Coriolis effect a few times, but what is it exactly? Well, imagine shooting an arrow at a target. You would expect it to fly in a straight line, hitting the bullseye of the target directly. That's how wind would travel on a straight and direct path. However, the Earth rotates, which means now we have to imagine our targets are rotating too. Imagine that same target was rotating around you. If you shot the arrow straight at the target, it would miss because the target would have traveled past that direct straight path that the arrow was on before it even got there. It would look like the arrow traveled at an angle past the target, and you may even think it didn't travel in a straight line. However, looking from above, like in outer space, you would see that the arrow did indeed travel in a straight line, even though it missed the target. This was actually something that naval officers were struggling with during a missile target practice back in the day. This optical illusion is what's known as the Coriolis effect. Since Earth rotates, wind doesn't cross areas we would expect it to in a straight path, but rather into areas at an angle from its origin. This explains why winds in the Hadley cells don't travel north to south, but rather northeast to southwest. In terms of Earth, we see winds in the northern hemisphere deflect to the right, and the opposite in the southern hemisphere. Those air masses move to the left. That alone doesn't determine the direction of the wind, though. This is due to a combination of things, including the Coriolis effect we just discussed, but also friction in the pressure gradient system. Friction can slow down the speed and change the direction of the wind. For example, wind moving over the mountains and rough surfaces of Earth move way differently, usually slower, than wind that would move over smooth, glass-like areas like the ocean waters. Now that we understand what wind is, along with how and why it moves in the way it does, let's talk about how it impacts the climate in different areas and at different times of year. The high and low pressure areas generally determine the amount of precipitation an area gets. In the winter months, high pressure systems typically form on land. When there are high pressure systems in the area, the air begins to cool and sink, typically causing a dry and cold environment. This is why when we look at the map, we see that in the middle of the US, the winters are colder and drier. This also explains why in the winter, some of us feel like our skin is drier or our lips are more chapped. As the air moves across to the southwest, we know that it heats up from the Earth's surface and rises, creating low pressure systems and evaporation. As air collects moisture and rises, it cools and condenses. This leads to cloud formation and precipitation, which is why the winters become more wet and mild in places as it moves southwest. In the summer months, we see the opposite occur. Low pressure systems form on land. This causes cloud formation, and it is common to see more rain and humid air where it was once cold and dry in the winter. I hope this help explains how Earth is circulated and why the circulation is important to understand.